In the last lecture, we have seen the definition of connectedness. We have also seen some examples of connected spaces and spaces which are not connected. And in this lecture today, we will see some general conditions for a space to be connected. So this is for arbitrary topological spaces. And the first result in this direction is given by the following theorem. So this theorem says that if A alpha in J is a collection of connected subspaces of a topological space. So the first theorem in this direction is the following theorem. So in this statement, we take a collection of connected subspaces. So it's a collection of connected subspaces A alpha of a fixed topological space X, and we assume that the intersection of all these A alphas is non-empty. So they have at least one point in common. And then the statement says that the union is a connected subspace of X. So let us see a proof of this theorem. So to prove the theorem, we proceed by contradiction. So we suppose that UV is a separation of the union of all the A alphas. So then since intersection of all these A alphas is non-empty, so there exists some point P in this intersection. Okay, so this is a point in the intersection of all these A alphas. So then either P belongs to U or P belongs to V, but not both, since not both, since U intersection V is assumed to be empty. So either P belongs to U or P belongs to V. Now since P belongs to A alpha for each alpha in J, and then we have already seen that if you have a separation for a larger space and if you have a subspace, then the subspace must lie in one of the separated sets A or B. So we are going to use this. So then if you take some A alpha, then P is in A alpha for each alpha, and then A alpha is a subset of U, or A alpha is a subset of V for each alpha. So if you choose P to be in U, then all the A alphas are subsets of U. If you choose P to be in V, then all the A alphas are subset of V. So then this implies that the union alpha in J of the sets A alpha is a subset of U, or the union is a subset of V, which contradicts the fact that the union of the A alpha is precisely the union of U and V, and U, V are non-empty and disjoint. So we see that we have reached a contradiction, and this means that there is no separation of the union, and so it is connected. So a union of connected subspaces with at least one point in common is connected. Now let us move to the next property. Now the next result is an important one, and it is a theorem about images of continuous functions, and it says that if x is connected and f is a continuous function from x to some other topological space y, then the image f of x inside y is a connected subspace of y. So in words, images of continuous functions on connected spaces are connected. So let us see a proof of this theorem. So as always, most of these theorems are best proved using the argument of contradiction. So let us proceed with that. So suppose that fx is not connected. So this means that there exists a separation AB of fx. So what are A and B? So A and B are non-empty open subsets of fx. Open subsets of fx. So now here we have already seen in the previous lecture that a separation of a subspace is taken in the sense of the subspace topology. So here A and B are open in the subspace topology of fx, right? And fx is a disjoint union of these two sets. Now because fx is f is continuous, since f is continuous, we have f inverse u belongs to the is an open set in x if u is an open set in y. So now we are going to see what are f inverse of A and f inverse of B, these sets from the separation that we have of fx. We want to see what the inverse image of these sets look like. So now since A and B are open, we have seen that A and B are open in the subspace topology of fx. So there exists u and v. So let me write u and v here. U and v open sets in y such that A can be written as u intersection fx and B can be written as v intersection fx. And u and v must be disjoint because A and B are disjoint. So u intersection v is empty, and of course u and v are non-empty themselves. Because A and B are non-empty, u and v are also non-empty. So now we compute the pre-image of A. So pre-image of A is f inverse of u intersection fx, but this is nothing but f inverse of u, and because u was open in y, this is open in x. Similarly, f inverse B is equal to f inverse v, and this is open in x. And now we have x is the union of these two sets, f inverse A union f inverse B, and both the sets are non-empty. Both f inverse A and f inverse B are non-empty open. We have seen that they are both given by open sets, and their union is X, and union is X, which is the same as saying that F inverse A, F inverse B is a separation of X, which is a contradiction to the fact that X is connected. To X being connected. So we see that images of connected subspaces under continuous maps are connected. Now we have an immediate corollary. So corollary is a consequence of our theorem, and this is that if F between two spaces X and Y is a homeomorphism, then X is connected is equivalent to saying that Y is connected. And the proof is very easy. This is because Y equals F of X and X equals F inverse of Y. Note that, remember that a homeomorphism is a bijection, and with both F and F inverse being continuous functions. So Y equals Fx and X equals F inverse Y. So for example, if X is connected and F is continuous, then Y equals Fx is connected from the previous theorem. And similarly, if Y is connected because F inverse is continuous, so X, which is F inverse of Y, is connected. So this corollary is quite easy to show. The next result is about connectedness of subspaces which lie between a connected set and its closure. So here we have A and B, which are subspaces of X, and B lies between A and A closure, which means that B has some or all of the limit points of A along with all points of A also. So the statement says that B is connected if A is connected. So let's see a quick proof of this fact. So again we use the contradiction. So suppose that B is not connected, and let B1, B2 be a separation of B. Now we have seen in one of the previous lemmas that then because A is connected, it must lie entirely within B1 or entirely within B2. So this is lemma. So from lemma 1.2 in lecture 1 of this week, we have that either A is a subset of B1 or A is a subset of B2. So suppose A is a subset of B1. If A is a subset of B1, this implies that A closure is a subset of B1 closure. However, B1 closure intersection B2 is empty, as we have seen before for the connectedness of subspaces. The closure of one does not intersect the other set from the sets which form the separation. So now, because of this means that B intersection B2 is empty because B A is a subset of A closure, since B is a subset of A closure. So this contradicts the fact that B2 is non-empty. This contradicts the fact that B2 is non-empty in B. So we have a contradiction, and so B is connected. Now the converse of this statement does not hold. So remark, the converse is not true. Converse of the above theorem is false in general, and an important example in this, an important counterexample for this is the case when x equals, well, let me write A and B. So x equals R, A equals the rationals, and B is the same as R, and this is the same, A closure is also R. We have seen that the closure of the rational numbers is the whole real line, and so with this we have A lies in B, which is actually the same as A closure in this example. Now we will see shortly that the real line with the standard topology, of course, is connected. Okay, but we have already seen, but the rationals is not connected as a subspace of the real line, as a subspace of R. This we have already seen. So this means that the converse does not hold. And now we will go to connectedness of arbitrary Cartesian products of connected spaces. So in this theorem, we consider an arbitrary collection x alpha of connected topological spaces. So each x alpha is a connected topological space, and then we take this arbitrary collection, arbitrary Cartesian product of all these x alphas, and the claim is that it is connected in the product topology. So we have seen there are two possibilities to give a topology on the arbitrary Cartesian product. Either we can give it the box topology or the product topology, and in this theorem we will consider the arbitrary Cartesian product with the product topology, and if all the x alphas are connected, then the arbitrary Cartesian product is connected in this topology. So before we go to the proof of this theorem, let me give a definition of what are called open maps. So what is an open map? So if f is a function between topological spaces x and y, then f is called open if and only if u is open if u is open in x. So if u is open in y if u is open in x. It means that it pushes open sets to open sets. Now for a continuous function, we have seen that a continuous function pulls back open sets to open sets, and this open map is the other way around. It pushes open sets to open sets. Now let us see an example of such a map example. So take two topological spaces x and y, and let let x cross y be given the product topology, because this is a finite Cartesian product. It does not matter whether you give it the box topology or the product topology, because we have proved that they are the same. Now the coordinate projection maps, then the maps pi1, which is the coordinate projection onto the first coordinate, and pi2, which is the coordinate projection onto the second coordinate, are open maps. So to see this, suppose that, so this is a short proof, suppose that U is open in x cross y, and let for example, just to show that pi1 is open, the other case is similar. So let x belongs to pi1 of U. Now if we can show that there exists an open set V of x such that x belongs to V and it is a subset of pi1u, then this will imply that pi1u is open. Now to show this, let us take any y, any point y in Y, and consider the point x, y belonging to the set U. Okay, so we consider a point x comma y. So remember that x was the point chosen in pi1u, so there exists such a y such that xy belongs to U. So now we can, because U is open, since U is open, we can use the basis description of open sets in the product topology. So there exists a basis element B, which is of the form V cross W, where V is open in X, W is open in Y, and we have the point xy belongs to B and it is a subset of U. But then if you just take the pi1 of B, but then pi1 of B is equal to V, because you are just considering the pi1 on a Cartesian product of two sets. So pi1 of V cross W, pi1 of V cross W is V, right? And we have X belonging to V, and this is a subset of pi1U, as B is a subset of U. So we have found an open set containing X and contained in pi1U. So this implies that pi1U is open. Similarly, pi2U is also open for the coordinate projection onto the second coordinate. So these are examples of open maps, and in fact we can also generalize this to arbitrary Cartesian products. So the coordinate projection maps, let's say pi beta, from the entire Cartesian product to x beta. So here taking beta in as one of the points in J, then these are defined as simply, if you take the J tuple notation, then pi beta of x alpha is just the point x beta. Okay, so these are open for each beta in J. So of course in the product topology, so the proof is quite similar to the finite Cartesian product case, and I leave it to you as an exercise to show this. Just remember what are the basis sets in the product topology, and just as we chose the basis sets in the finite Cartesian product, you can do the same argument here as well. And now we come to the proof of the main theorem. So proof of theorem 3.4. So suppose again we can use an argument of contradiction. So suppose that the arbitrary Cartesian product is not connected. So this implies that there exists a separation, A comma B of this space. So this was our X, and so here again A, B are non-empty, A and B are open in the product topology. So this is the product topology on the arbitrary Cartesian product X, and X is the union, disjoint union of these two sets A and B. So now A and B themselves are sets, subsets of the arbitrary Cartesian product. And now we make two important claims. The first one is that the image of pi alpha of under A and B are non-empty for each alpha in J. And secondly, that pi alpha A intersection pi alpha B is empty for at least one alpha. Okay, so for at least one alpha in J, the images pi alpha A and pi alpha B must be disjoint. So the first one is easy to show because well, A and B are non-empty, and pi alpha are the continuous functions in the product topology. So in fact they are non-empty even if you do not consider continuity into account. The image of a non-empty set is non-empty. So for one, this is because each set, well, let me just write A and B are non-empty, and image of a non-empty set under a function is non-empty. This is by definition almost. And now for the second part, for 2, suppose that again we use contradiction. So suppose that pi alpha A intersection pi alpha B is non-empty for all alpha in J. Okay, so this implies that there exists X alpha belonging to this intersection pi alpha A and pi alpha B. Now this is a point X alpha is a point in the capital X alpha, which was our topological space from the arbitrary collection of topological spaces. So this is for each alpha in J. Then the J tuple given by X alpha, so let me denote this X alpha hat. So this x alpha hat, alpha in J, this belongs to A intersection B, right? Because then we will have, so, but this contradicts the fact that A intersection B is empty. So this contradicts the fact that A intersection B was empty because AB was a separation for X. And this implies that, so this actually implies that pi alpha A intersection pi alpha B is empty for at least one alpha in J. And now that we have these properties, we will use them to produce a contradiction for the fact that each of these x alphas must be connected. So because this is these two sets are disjoint for at least one alpha, so say alpha equals alpha naught, for alpha equals alpha naught, this holds. So then pi alpha naught A is open in x alpha naught because pi alpha naught is an open map, and similarly pi alpha naught B is also open in x alpha naught, and they are non-empty. We have seen from the first claim that they are both non-empty. Now we have proved that they are both open, but also we have shown that these are disjoint. But since X is the union of A and B, this implies that x alpha naught is the union of pi alpha naught A and pi alpha naught B. But now we have produced two open sets which are non-empty, open, they are both open, and disjoint, whose union is x alpha naught. But this means that this is a separation for x alpha naught. So let me write that down. This means that pi alpha naught A and pi alpha naught B is a separation for x alpha naught, and this is a contradiction. This is a contradiction since we have assumed x alpha naught to be connected. So this proves our result that x alpha, the Cartesian product of all these x alphas, is connected in the product topology. Now let me end with a remark, which is that the above theorem does not hold for the box topology. So we have considered the arbitrary Cartesian product in the product topology, but if you have a collection of connected subspaces, then the arbitrary Cartesian product, when it is given the box topology, may not be connected. So a counterexample for this, or rather an example where this happens, is when you take xn to be R for all n in the natural numbers, and then consider the Cartesian product R omega, which is the Cartesian product over the natural numbers of all these xn's with the box topology. Box topology. So we consider this. So now any point x in R omega is a sequence. We have seen this before, and x can be written as a sequence xn, where n is in the natural numbers. So now let me define what are bounded and unbounded sequences. Bounded and unbounded sequences. and the collection of such things will actually provide a separation for the space R omega in the box topology. So a sequence is bounded, a sequence xn is bounded if, so of course this is in R, if there exists real numbers small r and capital R such that we have R less than or equal to xn less than or equal to R for all n in n. So we have this is called a lower bound and this is called an upper bound for the sequence. And if a sequence has both an upper bound and a lower bound, then it is called bounded. And if either the lower bound or upper bound doesn't exist, then we call it as unbounded. So a sequence which is not bounded, is called unbounded, which basically means that it either goes off to plus infinity, the xn's go farther and farther away to plus infinity, or the xn's go farther and farther below to minus infinity. So now take the two sets U, this is the set of all bounded sequences, and V the set of all unbounded sequences. So of course both are in R. Now both U and V are non-empty because we can explicitly write down some members of U and V. So for example, the sequence 1 over n, n in n, is bounded because we have 0 less than equal to 1 over n less than or equal to 1 for all n in n. And the sequence n itself, so here for the first one xn equals 1 by n, and here xn equals n. So this is unbounded because if you have an upper bound, for example, for this, then it contradicts the fact that you have infinitely many natural numbers in this sequence. So so we have explicit elements of U and V, so they are both non-empty and both U and V are open. So for example, first of all, that U intersection V is empty, so of course a bounded sequence cannot be unbounded and vice versa, so they are disjoint sets. And the point is that both U and V are open because for any point xn in R omega, we consider the open set in the box topology, given by the product of so this is the infinite product of the sets xn minus 1 and xn plus 1. So this is the open interval xn minus 1 to xn plus 1, and you take the infinite Cartesian product of such intervals. This is open in the box topology, and we have that if xn is so let me call this W. So if xn belongs to U, then W is a subset of U, and if xn belongs to V, then W is a subset of V. So you can check that directly. that it is an open set in both cases, whether you have bounded sequences or unbounded sequences. So both u and v are open, and of course we have our omega is the union of u and v, because well, they are complements of each other. So these are open, non-empty and disjoint sets whose union is r omega, which means that uv is a separation of r omega, and so r omega is not connected in the box topology, not connected in the box topology. So we see that even though R is connected, as we will shortly see, the infinite Cartesian product under the box topology of connected spaces is not connected. So even though R is connected. So this is an example where the previous theorem fails for arbitrary Cartesian product of connected spaces when it is given the box topology.